Trigonometry, Chapter 2, Acute Angles and Right Triangles, Section 3, Approximations of Trig Function Values, Video 5, Application, Breaking Distance. The series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned about the formula that calculated the radius of curvature for a highway based on the superelevation, inclination of the curve, and the highway, and the speed of the car. In this video, we calculate the braking distance required to decelerate a car, or negatively accelerate it. If aerodynamic resistance is ignored, the braking distance d in feet for an automobile to change its velocity from v1 to v2 in feet per second can be modeled by the equation d equals fraction on the top 1.05 times v1 squared minus v2 squared. In the denominator, 64.6 times the quantity k1 plus k2 plus sine of theta, where k1 is a constant determined by the efficiency of the brakes and tires, and k2 is a constant determined by the rolling resistance of the car, and theta is the grade of the highway. Full disclosure, I do not know how to calculate k1 and k2, but in a problem like this, they would be given to us. For example, calculate the number of feet required to slow a car from 70 miles per hour to 50 miles per hour while traveling downhill with a grade of theta equals negative 3.5 degrees. Let K1 equal 0.4 and K2 equal 0.02. Well, this is almost a direct plug and play. Plug into this formula and then calculate it. But remember that our formula requires our velocities to be in feet per second. These are given in miles per hour. So just like before, we're going to have to convert both speeds to feet per second. Now, we could do the individual unit conversions like we did in the previous video. In other words, we could do that. Okay. But remember when I said memorizing 60 miles per hour equals 88 feet per second is handy? Here's a case where it's handy. We can just take the first velocity of 70 miles per hour and multiply it by this ratio. 88 feet per second, FPS, is equal to 60 miles per hour. The miles per hour would cancel, leave feet per second, and give us approximately 102.67 feet per second. So we can convert the ratio of units in one move as opposed to converting the individual units one at a time. And we could do the same thing for the second velocity of 50 miles per hour, multiply it by 88 feet per second over 60 miles per hour, and get 73.33 feet per second. And now we substitute all the values into the formula. Here's the formula. There's the value with the two velocities in feet per second substituted, and the values of the k's and the inclination, which was negative because we're going downhill. And when we do the math, we end up getting d is approximately 210 feet. So it takes 210 feet to decelerate from 70 miles per hour to 50 miles per hour under these conditions on a road with a negative grade of 3.5 degrees. That's what I just said. Now, why did I pick 70 and 50? Because I drive Highway 80 in Texas quite a bit. And as you approach the small towns, the speed limit drops from 70 to 50. So keep this in mind the next time you approach a small Texas town on a state highway. You need about two-thirds of a football field's length to slow down to the correct speed, assuming your car meets these parameters and the grade is negative 3.5 degrees. Now you try. Pause the video and try the following. Suppose the same vehicle with the same parameters, the same Ks, is traveling 90 miles per hour when it tops a hill and starts down a grade of negative 3.5 degrees. The driver spots a stalled car about 300 feet ahead. What distance would be needed to come to a complete stop? In other words, second velocity is 0 miles per hour. I'll give you a hint. It's more than 300 feet. Bonus challenge. How fast would the driver be going in miles per hour when he hits the stalled car, assuming he brakes when he's 300 feet from the stalled car? Pause the video, try the first one. I challenge you to try the second one. Okay, here's your fair warning. Solutions in 3, 2, and 1. And like the previous video, I am going to go over at least the bonus part of it. But as far as the how long does it how many feet does it take to stop from 90 miles per hour to 0 miles per hour under these conditions? If you convert the 90 miles per hour to 132 feet per second and substitute that for the V1 and 0 for the V2 because we're trying to stop, and then do the calculations, the answer is 788 feet. That's more than 2 football fields. If you're driving 90 miles per hour and you need to screech your brakes to a stop, you need a long distance to do that. He's not going to be able to stop in time. As far as the bonus question, how fast is he going? If he brakes when he's 300 feet away and then he hits the car, well, we have to substitute 300 for the braking distance, and because it's a change of velocity, so the braking distance will be 300, and we don't know the second velocity. This becomes a big algebra mess, but like I did in the last video, I would recommend solving for V2 first and then using the calculator. So the solve would go like this. First, we would multiply both sides by the denominator. That would put, come on, that would put this next to the 300, and it would look like this. And so we have that equals the 1.05 times the subtraction problem on the right. Now, the next move I would do is I would divide both sides by this 1.05 because that will get me closer to getting the V2 by itself. And if we divide both sides by that number, we get this fraction on the left is equal to the subtraction problem. Now, when you're solving an equation and the thing you're solving for is on the second half of a subtraction problem, there's a trick to getting it by itself, and that trick is to switch the second half of the subtraction problem with whatever's on the other side. It's basically moving this from the left to the right and changing its sign so it becomes negative, but moving the V2 squared from the right to the left and changing its sign so it becomes positive. It's what I call a switch to get something out of the second end of a subtraction problem. And now the only reason the V2 isn't by itself is because it's got a square. So square root both sides and we get this gigantic mess. And again, if you're thinking, I'll just figure out what those values equal earlier, meaning way back here, I'll figure out this denominator, I'll figure out 132 squared, I might distribute. I mean, you can do all those things, but anything where you round creates an error in the correct answer. And when you're building things for safety purposes, you want to not introduce an error while you're still doing calculations. You want to wait until the last possible moment, which is why I didn't use a calculator until the very end. This I would put into a calculator to get approximately 103 feet per second for the velocity upon impact, which converts to 70 miles per hour. Let that sink in. You're topping a hill, you're going 90, there's a stalled car in front of you 300 feet away, you slam on the brakes. Under these parameters, you're not going to avoid a collision. You're going to hit that car going 70 miles per hour and somebody's about to die. So the moral of the story is slow down, please.